the first example I usually talk about is pretend you threw a rock in a pond. I imagine everyone has probably done this at some point in their life, or at least has seen ripples. They form circularly, they move outwards, and they increase in size. So let's look at this example. Related rates. So suppose the radius, spelling really good, of a circle is increasing at a constant rate of 2 feet per second. How fast is the area changing when the radius of the circle is 10 feet? Or maybe even what if it was 20 feet? Okay, so that's our setup. And the idea here is that, and the reason it's called related rates is because we really have rates that are related. We're being told that the radius is changing at some rate, right? 2 feet per second. So it's getting larger and larger every second. We're being asked, what's the rate of change of the area at some particular moment? And just to give you kind of an idea what's happening here, right? So if you throw this rock in the pond, after 1 second, the radius should be 2 feet. So here's after 1 second, you've got this small circle where the radius is 2 feet. And then after another second, you've got this larger circle, right? The radius is now going to be how much? How much is it going to be? Right, exactly, right? Because it's growing 2 feet per second. So after 2 seconds, it's going to be 4 feet. And then at 3 seconds, it's going to be 6 feet. And then at 4 seconds, it's going to be 8 feet, and so on. So hopefully everyone's cool with the fact that what's happening here, what we can think about happening here is that every second, the radius is growing by 2 feet. So it totally makes sense to say that the rate of change of the radius, or what I'm going to call, if r is the radius, I'm going to say that dr dt is 2 feet per second. And I will mention here that almost always when you're talking about related rates specifically, almost everyone uses this Leibniz notation, right? We almost never write r prime. We almost always write dr dt when you're talking about related rates. I don't know why exactly specifically we've decided to do this, but there are some benefits to it. Okay. Now, what I want you all to see is the rate of change of area isn't the same every second. From time equals 1 to time equals 2, well, let's see. Let's actually calculate the areas before we talk about the rate of change. So time equals 1, the area is pi times 2 squared, so 4 pi. And at time equals 2 seconds, the area is pi times 4 squared, which is 16 pi. And then here it's going to be 36 pi. And here it's going to be 8 squared is 64 pi. So notably, the amount the area is increasing by is different every second. Right? From time equals 1 to time equals 2, the area increases by 12 pi square feet per second. So we're going to go up by 12 pi square feet. But here, from here to here, we're increasing by a different amount, right? In this 1 second, we're increasing by 20 pi. And in this 1 second, we're increasing by 28 pi. So the rate of change of area, unlike radius, is not constant. Right? You don't have, we can't just say that dA dt is equal to some constant number all the time. It is not. And that makes sense, right? Because if you make the circle 2 feet larger on the outer part, right, you're essentially kind of adding on the outside. And when you add on the outside, it's a lot more circumference to kind of add area to. Okay, well, that's enough kind of exposition there. What are we actually going to do to solve this? So here's kind of my usual process. Step 0, draw a picture if it makes sense. Draw a picture if needed. I feel like for a circle, you probably don't really need a picture. We know what a circle looks like. I mean, I guess we can draw it if we want to. There's our circle. And I should point out that when you're drawing the picture, the thing you want to really be aware of is you want to label the things that are changing with variable names. Meaning, since the radius is increasing, even though I know I'm interested in the moment when the radius is 10 feet, I'm going to call it R because it's changing. Okay. We'll have some other examples where it actually makes more sense to draw a picture. The first step after you've drawn a picture, or not, is to identify what is changing. Now, there are actually a lot of answers to this particular question. There are many things that are changing. In this circle, if the radius is getting larger, the radius is changing, the diameter is changing, the area is changing, the circumference is changing, pretty much any feature of the circle is changing. So we need to be a little bit more specific about what we mean here. When we say identify what's changing, what we really want to know is what have they told us is changing and what do we want to know is changing? So known and want to know. They've told us how the radius is changing, right? They said the radius was increasing at 2 feet per second. So we're going to say, okay, the radius is changing. We're going to write dr/dt, the rate of change of the radius as time is changing. That's going to be 2 feet per second. And then they're asking us, how is the area changing at some particular moment? I'm going to write that as dA/dt. I guess I should be a little right. I'm saying that R is the radius, A is the area, right? There's not a big leap, but we should be specific with our variable names. We don't know how the area is changing, right? That's what we were trying to find. Let me ask you all a question. After we find how the area is changing, what are the units going to be? If we're measuring the rate of change of the radius in feet per second, the rate of change of the area should be what? Or it should be what units? That's correct. Yeah. I see some right answers on Zoom. Anyone in class want to venture a guess? It's not feet per second. It's feet squared per second. And whenever it's an area, it's always some unit of length squared. Just like you measure the area of a house in square feet, or you measure the area of land in maybe square miles. People use acres, but really acres is just a measure of square feet. So area square, units, and volume is cubic units. So if I want to know how much volume was in this room, I might measure how many cubic feet there were. So the nice thing is you can totally plug in the units as you go, but the better option usually is to not and just say at the end, oh, I know what they're supposed to be. I'll kind of show you both ways. So there's step 1, identify what's changing. Step 2, I guess so I should point out the other thing that's also changing that we're not going to write down is changing is time, right? Time is definitely moving forward. Step 2, write an equation. Write an equation that relates all of the variables that we just identified. Ideally, you'll be able to write an equation using the variables you have in step 1 and nothing else extra. That's not always going to be an option. Sometimes you have to have an extra thing in there that we don't really want. Specifically, the case I'm referring to is when we have a cone. Cones often have extra things we don't really want, but we'll deal with it. Usually this is just going to be some sort of geometry formula. In this case, it's literally just the area of a circle formula. Area equals to pi r squared. That's it. Step 3, differentiate both sides. I should be a little more specific here. Differentiate both sides with respect to time. It's not always 100% of the time. Sometimes the variable that both things are a function of something else, but most of the problems we deal with are where things are changing as time is changing. Okay, so here's the thing I have to remember. Area and radius are both functions of time. So you could totally, if you wanted to, write this as A of t equal to pi times r of t squared. Here's what you should really think of though. Area is some stuff that's a function of time. Radius is some stuff that's a function of time. And when I take the derivative of them, I'm going to do it using implicit differentiation, aka the chain rule. So when I take the derivative of area, what do I get? I get the derivative of area. Right, the derivative of area is the derivative of area. Okay. When I take the derivative of pi times r squared, the pi constant hangs out. And let me ask you all, what's the derivative of some stuff squared? Let me ask you a different question. Let's take a real quick detour. If I said, what's the derivative of x cubed plus x quantity squared, we would know that it was equal to what? I've got some stuff squared. The derivative is 2. Go ahead. Exactly. 2 times the stuff to the first power, which we never say, times the derivative of the stuff. That's exactly what we're going to be doing over here. The derivative of some stuff squared is 2 times the stuff to the first power times the derivative of the stuff. You can also think of it like implicit differentiation, where r is implicitly a function of time, and the derivative of r squared is 2r times r prime. Okay, now that we have this equation, step 4, we're going to just plug in and solve. So I'm trying to find out what dAdt is. I know what drdt is. So I'm going to plug in and get dAdt equal to, let's see here, it's going to be 2 times pi. Oh, I had 2 different situations. I had one where the radius was 10 feet and one where the radius was 20 feet. So let's first do the one where the radius is 10 feet. So I'm going to get, let's see, dAdt is 2 pi times 10 feet, and then drdt is going to be 2 feet per second. Notice when I plug in the units, they are going to turn out to be what they should be. Right? I'm going to have feet times feet per second, which is feet squared per second. So that's going to end up being 2 times 10 times 2 is 40 pi feet squared per second. So when the radius is 10 feet, the area is increasing at 40 pi square feet per second, which is 120 something, right? Because it's 40 times pi. On the other hand, when the radius is twice as big, so the radius is 20 feet, we're going to get the rate of change of area is going to be 2 pi times 20 feet times 2 feet per second. And that's going to be 2 times 20 is 40 times 2 is 80 pi square feet per second. Notice I didn't write the units in there because I knew at the end the units were still going to be square feet per second. So you don't have to write, and I usually don't write the units in when I'm actually doing the multiplication. I just wait till the end and write what I know the correct unit is supposed to be. So questions about this? So the bigger the circle gets, the faster the area is increasing, right? If the radius was like 100 feet, and small increase in radius there gives you a lot more area at the end than an increase when the radius is small. We're going to do a lot more examples, but it's always going to be the same process. We're going to draw a picture. We're going to figure out what's changing. We're going to write down an equation relating those things. We're going to take the derivative of both sides, and then we're going to plug in and solve for what we want to solve for. Always kind of the process. Let's look at another example. Let's say we have the following. Yeah, sure. The radius of a cylinder is increasing at 3 inches per minute. And the height is decreasing at 4 inches per minute. Kind of a weird thing to have a cylinder change shape like that, but it can happen. How fast is the volume of the cylinder changing? Now that's not enough of a question. I have to give you more information. I have to ask how fast is the something changing when the radius is 8 inches and the height is 5 inches. So typically when someone's asking a related rates question, come on and can I see your symptom survey, please? So whenever someone's asking a question like this, they always have to be like, how fast is something changing when we're at this point in time or this measurement of the shape? You have to have that kind of information. There are a couple exceptions to that, but generally they're still going to give you that information. So let's draw a picture. Here's my cylinder. And again, things are changing. I'm going to label them with variable names. So here's my radius. And here's my height. And not that we really need to, but you could indicate, okay, we know that the radius is getting bigger. So right where this thing's going to be like moving out this way. You wanted to think about that. Thank you so much. But it's going to be shrinking this way, right? This part's going to be going like down. Right, so it's going to be smooshing that way, but getting wider that way. Okay. Not that you need to know that really. So step one. Let's go ahead and find what's changing and what we want to know is changing. So they're telling us how both the radius and the height are changing. They're telling us that dr dt, the rate of change of the radius with respect to time, is 3 inches per minute. And they're telling us that the height is decreasing at 4 inches per minute. So it's not going to be correct to say that dh dt is 4 inches per minute, because that would mean that the height was getting bigger by 4 inches every minute. We need a negative sign. So if something's decreasing, its derivative should be negative because its rate of change is negative, right? It's getting smaller and smaller and smaller. Its rate of change is negative. And then we're being asked to find how the volume is changing. It might even be worth writing down how the volume is changing when the height equals 5 and the radius equals 8. Just so we don't forget about that. That's what we want to find. How is the volume of the shape changing, or when the height's 5 inches and the radius is 8 inches? Okay, so after we have identified all the things that are changing, radius, height, and volume, and that should be right. Again, there are lots of other things that are changing. The surface area of the shape is also changing. No one has asked about that, so we're not going to worry about it. We're going to write an equation relating those things. And it's usually going to be the area or the volume of the shape. Sometimes it's similar to triangles, sometimes it's Pythagorean theorem, but it's almost always some sort of geometric formula. Like really, almost all the time. There are some examples that are not like that. Like for example, someone could totally ask a question. Well, in fact, maybe we'll do one like that in a minute. Yeah. There are other relationships like a BMI, for example. Someone says, how is your BMI changing when your height's increasing, your weight's decreasing? The equation isn't a geometric formula, right? There's an equation for BMI, which is like, it's some weird like height squared divided by weight or something like that. I don't exactly remember, but right, not everything is geometric, just a lot of our examples are. So let's see here. Our volume equation for a cylinder is pi times the radius squared times the height. Great, we've got all the variables we want and then nothing we don't. So now we're going to differentiate both sides. The derivative of volume is the derivative of volume, or the rate of change of volume is the rate of change of volume, right? But I really want to emphasize the derivative of volume isn't one, because we're not differentiating with respect to V, we're differentiating with respect to time. We're always, not always, we're almost always differentiating with respect to time. On the right-hand side, we're going to have to use the product rule because I've got a product of two different variables that are both changing. So on the right-hand side, I'm going to have, let's see, I'm going to treat this pi r squared as one piece just because the pi is next to the r squared. So I'm going to say that's one piece of my product. There's the other piece of my product. The derivative of pi r squared is going to be 2 pi r times dr dt. Or 2 pi times some stuff times the derivative of that stuff, the chain rule, times h, right? Do the product, and then vice versa. Leave the pi r squared alone. And what's the derivative of h? Yeah. Here's a good tip. When you're doing this process, the derivatives you know and the derivatives you want to know should all show up. If these three things don't show up after I differentiate, I've probably made a mistake. Okay, so then we're going to plug in what we know, solve for what we want. So let's see, I'm going to have, I want to solve for dv dt, that's nice. So dv dt is going to equal 2 times pi times the radius, which is 8 inches, times dr dt, which is 3 inches per minute, times h, which is 5 inches, plus pi times r squared, which is 8 inches squared, times dh dt, which is negative 4 inches per minute. Why do you treat your pi as your constant in this question, just like why did you not treat your pi? That's a fair question. So why didn't I treat pi as a constant in this question like last? I could have. So let me finish this up and then I'll address that question. But it's, yeah, so one second. So simplifying this, we're going to get, let's see, I'm going to do 5 times 2 is 10, 8 times 3 is 24, and 24 times 10 is 240. And then that's going to be, okay, fine. 64 times 4 is 256. So it's going to be minus 256 pi, which is going to be negative 16 pi. And what are my units this time? Well, everything was measured in inches per minute for how the height and the radius were changing. So this volume should be changing at, right, exactly, cubic inches per minute, or inches cubed per minute. If you wanted to, whoops, you could have thrown in the units in the problem, right? This was really 8 inches. This was 3 inches per minute. This was 5 inches. And then you have, oh yeah, inches times inches times inches, inches cubed per minute. Same deal here. This is 8 inches squared times negative 4 inches per minute. So you have inches times inches times inches per minute, which is still inches cubed per minute. The units should always work out to be what they need to be, which is why I'm generally of the opinion that if you know what they should be, because it's a volume per time, it's a whatever your unit is of length cubed per time. Sometimes people will ask you, like sometimes, so someone could be less than nice and ask you, what's the rate of change in cubic feet per minute? And then you have to do some terrible unit conversion stuff, which I don't particularly enjoy. Yeah, it'd be kind of awful here because so to change, so okay, fine. Twist my arm. If you wanted to write this answer in cubic feet per minute, so what's the rate of change in feet cubed per minute? Let me ask you first, very, very generally, is the answer going to be bigger or smaller than what I already found? It's going to be smaller, right? Because if you have this many inches cubed per minute, it's going to be way less feet per minute or feet cubed per minute, right? Because there's 12 inches in a foot. And so if you're measuring in feet, you're going to have less of them. Now, the thing is, my answer isn't just going to be divided by 12, because it's not just 1 foot per 12 inches. It's 12 inches per 1 foot times 12 inches per 1 foot times 12 inches per 1 foot, right? There's 3 conversions there. So if you actually wanted to change this to feet cubed per minute, here's what you would do. You'd say I've got negative 16 pi inches cubed per minute. And then you would multiply by 1 foot per 12 inches cubed, if you really wanted to change it to cubic feet per minute. So that answer would end up being negative 16 pi over 12 cubed cubic feet per minute, if you really, really, really wanted to do it. You don't want to do it that way, though. I mean, certainly, I should back up. You do want to do it that way if that's what they're actually asking you. Right? That's like the easiest way to change from one unit to the other. But it's no one should be asking this, I hope. It's kind of unnecessary. So somebody asked, and they're not wrong to ask, why didn't I just treat the pi like a constant out in front? I don't know. I don't have a good answer other than it's kind of the way I like to do it. But I suppose the better answer is we could have treated the pi like a constant out in front. So if you wanted to, you could have said, okay, volume is pi times r squared times h. That pi that's a constant multiple is just going to hang out. And the derivative is exactly pi times, okay, I'm going to take the derivative of this using the product rule. So it's going to be the derivative of r squared, which is 2 times r to the first times dr dt. And then we still have the h here. Plus, then you vice versa, r squared times the derivative of h, which is dh dt. It's still the same result, right? We're still getting 2 pi r times dr dt times h plus pi times r squared times dh dt. So it's still the same thing. I just find it, I don't know, I find it convenient to have the pi go with one of the terms as opposed to bringing out in front and treating it that way. But either way is totally legitimately fine. Other questions about this? So I will mention, it's kind of atypical to have an example like this where someone says the radius and the height are both changing in different ways. A more typical example of how you might see a problem with a cylinder is something like this. Yeah, a cylinder with a radius of 4 inches and a height of 12 inches is being filled with liquid at a rate of 10 cubic inches per minute. How fast is the height of the water changing when the container is half full? Okay. So we're gonna do this question, and then we're gonna do the same question, but for a cone-shaped container instead of for a cylinder-shaped container. And it's gonna drastically change the problem. So let's again draw our picture. Here's our cylinder. And it's got a radius that isn't changing, right? The radius is 4 inches. And it's got a height that isn't changing. It's 12 inches. But it's got water in it. And that water level is changing. So we're filling this thing with water. And the height of the water, which I'm going to give a variable name, is changing because it's going up and up and up as you fill this thing with water. And there is the water. Okay. So our question, well, in fact, I keep wanting to jump to the question. Let's go through the process, right? What's changing? So what's changing? What's one of the things that we care about that's changing? Anybody? The height of the water, totally. Do we know how that's changing? No, that's what we want to know, right? That's what the question is. How fast is the height of the water changing when the container is half full? Okay. What else do we know is changing? What's the piece of information they've given us? We're filling it with water at 10 cubic inches per minute. So we know how the height's changing, the area is changing, the volume's changing. If it's 10 cubic inches per minute, it's got to be a measure of volume, the rate of change of volume. So we know that the volume of liquid is changing at positive 10 cubic inches per minute. Right, we're adding that much volume every minute. Great, we've got an equation for the things that are changing. But now we need to relate those things. So we need an equation relating the volume of water or liquid, I said liquid, but whatever, water, the volume of liquid and the height of liquid. Okay, so we're trying to look at this kind of portion of it right here and ask, how do we write this? Well, it's still a cylinder shape. We're still gonna say, okay, the volume is still pi times the radius squared times the height. But now here's a little bit of a difference. Before I start differentiating both sides here, is the height changing? Well, it is. So, right, so because, right, so again, right, I want to be, but I should be more specific, right? I'm not looking at the whole cylinder. I'm looking at this cylinder of water or liquid. Right, that's what we're actually looking at. Is that cylinder's height changing? Yeah, because we're adding water to the thing. Is that cylinder's radius changing? No, we're just putting it in this other cylinder that is not getting wider and wider. So what we should do before we do this is we should say, oh, well, the radius is just 4 inches. So I'm going to rewrite that as 16 pi times h. And now we're going to differentiate both sides. The derivative of volume with respect to time is dv dt. And the derivative of 16 pi times h, well, we have a constant times a function. The constant hangs out. And the derivative of height is the derivative of height, dh dt. So now notice, it doesn't actually matter how full it was, right? I was going to point out that we needed to plug in that the height was going to be 6 inches, because that's how half full is. That's the height when it's half full. But there's actually nowhere to put that, which is okay. Because if you think about it, it shouldn't matter how full it is, right? If you're just adding water like layer by layer or slice by slice, it doesn't matter if you're at the very bottom or the very top, because you're still kind of adding, you're going to be increasing the height by the same amount because it's this shape that doesn't really vary as you go up or down. So we'd say, oh, well, that's going to be nice. That's going to be 16. Well, I should go to the next step. Fine. Last step, dv dt is going to be 16 pi times dh dt, which is, oh, so that's what we want. I plugged in for the wrong thing, right? I didn't plug in for the right thing. I should be plugging in for dv dt. So I've got dv dt being 10 equals 16 pi times dh dt. And then solving for dh dt, I'm going to get 10 divided by 16 pi equal to dh dt. And simplifying, I have dh dt equal to 5 over 8 pi. And what are my units going to be? Well, is it a measure of length, area, or volume? It's a measure of length. So it should be my units to the first, which is my units, which are my units of measurement are inches per minute. And it should be positive because the height of the water is increasing. You might, so if we look back at the equation for just a minute, you might be curious as to how we would actually get that. Because if you look at this here, it looks like dV dt is, right, that's going to be measured in inches cubed per minute. You might wonder how we're getting rid of the inches, like 2 of the inches there. Well, if you remember, right, we plugged in R equal to 4 inches. So right there, the 16 pi is really 16 pi inches squared. So that when we divide both sides by 16 pi inches squared, the inches cubed divided by the inches squared gives you just inches per minute. Cool. Questions? So this is kind of always the process. The process is always, or at least this is always the process that I have found that works pretty well for people. Is you figure out what's changing, you find an equation relating them, then you differentiate both sides, then you plug in what you know, solve for what you want. Let me go ahead and give me 1 second. I want to grab a different example just to kind of show you guys that it doesn't always have to be time. So I know I have an example over here. Just give me a second. Sorry, 1 moment. Come on. There we go. Where are you? Example? Oh, sure, we can do that one instead. That's not exactly what I was thinking of, but I'll do. Sure. Here's a non-time. Oh no, it's still a time example. I guess we like time. Time is a time. Sorry, I guess I don't have an example. Now I'm curious. Though. 1 second. Let's do this. Okay, so here's our. No, it's still like I'm trying to make an example that doesn't have time. It's still time. Like, so here's the example I was trying to think of that wasn't gonna have time in it, but not really. So here, so check this out. So let's say we know that for me, James is getting shorter, he's shrinking. Not really, I'm just making things up. And let's use the metric system. So let's say at 1 centimeter per year. And gaining a little weight. Let's say he's also gaining 2 kilograms per year. Notice there's time, right? I can't avoid the time. I feel like you might be able to do it, but it's not easy. How fast is his BMI changing when time equals 5 years from now? And I will tell you the BMI equation because you probably don't know it off the top. So like I said, most formulas we deal with are geometric formulas, but sometimes there are other things like BMI, or another good one is, where'd you go here? The like the Boyle's law that relates pressure, volume, and I'm not good at chemistry. Pressure and volume and something else. I think it's pressure and volume actually. So the BMI equation. Interesting. That's not that interesting. So here's the equation. It's BMI in the metric system is much easier than in the US system. The BMI is just your weight in kilograms per your height in meters squared. That's your BMI. I feel like I need to give you a little more information, right? Because there's something. Well, let's go with the problem, and we'll talk about what we're probably missing from this problem. So, step one. We can't draw a picture, right? There's no good picture. You can draw a picture of a person and be like, they're getting fatter and shorter, but that's not super helpful, right? So, step one, what's changing? Well, the height's changing. So the change in height is negative. I do want to use the right units. So instead of saying it's -1 centimeter per year, I'm going to say it's negative, well, it's 1 centimeter is 1/100th of a meter. So it's negative 0.01 meters per year. And then my mass, not my volume, not my weight, right? So I should be clear, it's not super important right now, but when you take physics, it's very important to differentiate between mass and weight. Mass is measured in kilograms, or in the US system measured in slugs, terrible unit. Weight, also known as force, in the metric system is measured with newtons, and in the US system is measured with pounds. So I know we often equate pounds and kilograms, like we have this conversion for them, and that conversion is true on planet Earth. But on the moon, I'm still the same 80 kilograms that I would ever be, because it's the same mass. But on the moon, my weight would be far less because the gravity, the acceleration due to gravity is different there. So weight is dependent on the force acceleration due to gravity. Mass is your mass wherever you're at. All right, so anyway, the change in my mass as time goes on is going to be, let's see, I'm gaining 2 kilograms per year. All right, so now we want the equation relating the things. So the equation, they already gave it to us. The equation is going to be BMI. Oh, well, we'll get it in a second. So BMI is mass divided by height squared. Again, mass in kilograms, height in meters. And I suppose I forgot to mention here, we know these things and we want to know how my BMI is changing. Okay. So now we're going to differentiate those things. So we're going to take the derivative of this. So dB dt. Yeah, I knew I forgot. So I'll point out what I forgot to tell you guys. We probably need to know how tall I am and how much I weigh to actually be able to answer this. Let me show you what I mean. If we differentiate this, we're going to have to use the quotient rule because both m and h are variables. So it's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom. The derivative of h squared is going to be 2 times h times dh dt. I could have made this easier probably. You guys know a way I can make this easier? I could have made my life easier. I could use the product rule instead. Or we could have done the derivative of m times h to the negative second plus m times the derivative of h to the negative second, which is going to be -2 times h to the negative third times dh dt. But either way, we have to know how tall I am and how much I weigh at the moment of interest. So what I really should have said, instead of how fast is his BMI changing when time is 5 years from now, what I really should have said is how fast is his BMI changing when his height is, I don't know, how tall am I in centimeters? Let's just say I'm 100, and let's say I'm 200 centimeters tall, or 2 meters. Even though that's a total lie, I'm definitely not 2 meters tall. Height is 2 meters, and his mass is 80 kilograms. Again, probably also not accurate. It's all right. So then we would just plug in all the stuff. So we'd say, okay, I'm going to plug in the MDT, which is 2 kilograms per year, times height to the negative second power. So that's going to be, let's see, height is 2 meters. Or it's not 2, yeah, 2 meters. So 2 to the negative second, that's going to be 1/4. What are the units there? Good question. I don't know. Because I don't really know the units for BMI, to be perfectly honest. Right? It's kind of a, I mean, I guess I do, right? It's literally kilograms per meter squared. So the units are going to be, when we find this thing, dBdt should be in kilograms per meter squared per year. Which is kind of interesting when you think about it. When you take a derivative of something with respect to time, you're just taking whatever the units are for that thing and dividing by the next unit of time. It's like when you talk about what your position is, you might measure it in meters. And then the derivative of that, which is velocity, is meters per second. And the derivative of that, which is acceleration, is meters per second per second. So every time you differentiate something with respect to time, you're just dividing by another unit of time when you're talking about the units. So I guess this, yeah, this would really be meters squared in the bottom here. Yeah, kind of funky. And then I was doing it this here. Plus the mass, which we said was 80 kilograms. And then we're going to have times -2 divided by the height cubed, the height being, yeah, see, the units are funky. 2 cubed. And then that's going to be times dH dt, which is, we said was something, -0.01 meters per year. I don't really care what the answer is here. We could totally find it if we really wanted to. 2 divided by 4 is 1/2. 80 times -1/4 is going to be 20 times 0.01 is 0.2. So we would end up getting 0.5 minus 0.2, which is 0.3. And the units are bizarre, but they do work. So I just want everyone to see the units do actually work. You get kilograms per meter squared per year. Same deal here. Kilograms times meters divided by meters cubed is per meter squared per year. So funky units. This is, again, another plug for saying, don't deal with the units until the end, right? If you know what your thing is measured in, its rate of change is whatever that thing is measured in per unit of time. And I do kind of think we're pretty much stuck with per units of time. Like there's no easy way to make it a problem where it's like something else. Someone asked, how do I get 1/4 meters squared? So when I was plugging in height here, I was plugging in, actually, so sorry, not here. I was plugging in the height here. I was getting 1 over the height squared, and the height was 2 meters. So I'm getting 1 over 4 meters squared. That's how I'm getting the 1 over 4 meters squared. Okay. So kind of a weird example, right? I mean, definitely a weird example. I just made it up, not gonna lie, right? It's a little bit weird, but still, there's this idea that you can have a function of things and we can find its rate of change by just differentiating everything and plugging what we know, finding what we want. Let's look at a more kind of standard example. Oh yeah, yeah. I said I was going to do the cone and then I got totally sidetracked by this other thing. So let's go back to the one we were doing before, but now we're going to change it around if I can move this piece of paper. And let's talk about this same example, but now we're going to make it a cone. And we're going to ask the same question. How fast is the height of the water changing when the cone is, well, I don't want to say half full because it's not really half full, but when the height of the water is half the total height. So when the height of the water is 6 inches. Let's go ahead and write it all out just so we don't like have to make it all up. Now we have a cone with a radius of 4 inches. I should say radius of the base. Oh, sorry, thank you. And a height of 12 inches. Is still being filled with water at the same rate, at a rate of 10 cubic inches per minute. And now the question is, once again, how fast, you can say the height of the water, you can say the depth of the water, they both kind of mean the same thing. How fast is the depth of the water increasing when the water is 6 inches deep? Okay, so same idea. Here's our cone. It's got a radius of 4 inches, it's got an overall height of 12 inches. And then we're filling it with water. So this height here, the height of the water, is definitely changing. And that's what we want to know about. So we want to know what dH/dt is. And we know that the rate of change of volume is 10 cubic inches per minute. And what we're going to do now is we're going to write the equation relating height and volume of a cone. And this is where we end up getting extra stuff that we don't really want that we have to deal with. Because the equation for the volume of a cone, right? And again, I'm talking about not the big cone, I'm talking about this cone here, right? The cone of water. The volume of that cone of water is going to be 1/3 pi times the radius of that cone squared times the height of that cone. And the problem is we don't know how the radius is changing, right? No one told us that. We could probably find it. It's actually very findable, but that's not usually the easiest way to deal with this problem. So here's what people usually do before they start step 3, where we differentiate both sides. We're going to eliminate the radius. And the way we're going to do that is by finding a relationship between the radius and the height of the cone. So let me ask everybody, if you look at the big cone, where the radius is 4 inches and the height is 12 inches, you could say the radius is what fraction of the height? 1/3. Great, you're good to go. The radius is exactly 1/3 of the height. And that's true whether it's the big cone or the little cone, because these cones are similar in proportion. If you really want to, and this is what people actually do, you could draw, if I cut this down the middle and just think about the triangle, you could totally draw the similar triangles, where this here is the radius of the cone. This here is the height of the cone, and this is 4 inches, and this is 12 inches. And then you could use similar triangles and say, okay, the base to the height equals the base to the height. And then you could solve for the radius and say, oh, multiply both sides by the height, the radius is 4/12 of the height, which is just 1/3 of the height. But I don't think you need to do all that work. If you can see that the cone has a radius that's 1/3 the height, that's your equation, right? You just have to say the words. Oh yeah, the radius is 4/12 the height. The radius is 1/3 the height. That's our equation. So we're going to plug that in for the radius there. So that now we can have the volume is equal to 1/3 times pi times 1/3 the height squared times the height. And then before we start differentiating, we're going to simplify this. This is going to be 1/3 times pi times 1/3 h squared is 1/9 times h squared times h. And then finally, 1/3 times pi times 1/9 is pi over 27. And h squared times h is h. And now we're ready to differentiate things. Hopefully not run out of room. So step 3, differentiate. The derivative of volume is dv dt. The derivative of pi over 27 times height cubed. The pi over 27 is a constant that just sticks around. The derivative of some stuff cubed is 3 times some stuff squared times the derivative of our stuff. Oh, it's like 10 minutes right now. Lots of memory. So we've taken the derivative of both sides. Now we're trying to solve for dH dt, because that's what our unknown is, right? We want to know what this is. So we're going to plug in 10 for that. And we're going to plug in the height equal to 6. So I'm going to have pi over 9 times 6 squared times dH dt. And then we're going to solve for dH dt. So I'm going to multiply both sides by 9, divide both sides by 36 pi. So I'm going to get 90 over 36 pi equals dH dt. We could probably simplify that. 90 and 36 both have factors of 9. That's 10 over 4. That's 5 over 2. So 5 over 2 pi inches per minute. This is especially true for cones. Whenever you have a cone shape, and not always, like, so I could totally ask a question like, how is the volume of this cone changing if the height of the cone is increasing by this much and the radius of the cone is decreasing by this much? And I could ask that kind of question. But most of the time when we ask cone questions, they're usually, you're filling this cone up at this much volume per time. And we're going to ask how the depth of the water is changing as you're filling it up. And typically we have to do this sort of thing where we replace the radius with what it is as a fraction of the height. The usual way this often works itself out. I need to go to the restroom. I'll take a quick break. I'm gonna fill up my water, go to the bathroom. When we come back, we can do more related rates. There's definitely more examples we can cover, or if you guys want to see other things, I know there are other things to see. So think about what you might want to see. Come back in a couple minutes. You all are welcome to use the restroom, get water if you need to, or just hang out for a couple minutes, chat, do whatever you want. I'll be right back.
You weren't helping me.
No,
No, and then she has to like, oh no, I don't. She has to like,
I really, I told you the same thing.
yeah, but
I did, I want to.
I'm still with the other one. Don't want that. The take of these. But it's part of it. But it's not. You know, the multiple. Yeah, some.
I really use this 9%. This and then two foot here, right? Like, it would be the first one.
There's a big pool full of. What is the pool you love for the body over? You're like, what? I don't know.
What? I think it's all right. It's just a-
Oh, yeah, but I was gonna come to it. I know they don't. Well,
All right.
Okay. More related rates. Okay, more related rates. I know I was looking at someone else's homework assignment. It looked like there was quite a few logarithmic differentiation types of questions. So if there are other things you guys want to see, you should speak up. Otherwise, I mean, related rates are important. They definitely come up. Let's do some more examples because there's certainly more examples I am aware of. So let's look at another kind of common example. That's one of my favorite questions. So yeah, we'll phrase it this way. Katie, who is 6 feet tall, is walking away from a street lamp. A 20-foot tall street lamp, I should point out. Can you not see? Okay. How fast is the length of her shadow increasing? Well, I should really say changing. When she is 10 feet from the lamp. All right. Well, let's draw a picture. So here's the street lamp shining bright. Here's the ground. Here's Katie. And here's her shadow being cast. Like that. And the thing we're interested in is the length of her shadow. So we should give the length of her shadow a variable name. But we also know that she is walking, right? She's walking away from the street lamp. And we know how fast she's, oh, do we know how, I didn't see how fast she was walking. That's an important piece of information we need to know. So if she is walking away from the lamp, the street lamp, at a rate of 4 feet per second. Great. So she's walking away from the street lamp at 4 feet per second. I need to write down what's changing. Okay, well, we certainly know the length of her shadow is changing, right? The further away she gets, right? So when she's like, you know, when she's way over here, the shadow is going to be doing, right, this kind of deal. And it's going to be much longer. All right, so as she moves to the right, the length of her shadow is definitely increasing. So we want to know what dx dt is. But typically we have to know something. We know how fast she's walking. But what am I going to call that? I probably need to label something else. I probably need to label the distance between her and the street lamp. Because if you have your distance to some stationary object, right, the street lamp isn't moving, your distance between, or Katie's distance from herself to the street lamp is changing at the rate she's walking at, right? If I'm, you know, if I say my distance from the board to whatever is some measurement, and I'm walking at a rate of 2 feet per second, my distance from the board to me is changing that. So I can say that, okay, I'm going to call this y, and we can say that dy dt is equal to 4 feet per second. And that's kind of actually a thing that something that gets overlooked a lot of the time is when you're told how something is moving. In a setup like this, you often have to say, okay, I'm going to call the distance from my object to a stationary thing some variable, and then say, oh, that variable is changing at the constant rate of movement. All right, now we need an equation relating them. I should probably label the other things too. Should label the not changing things, right? KD is 6 feet tall. This lamp is 20 feet tall. Okay. So now that we know what we want, or what we have and what we want to know, now we need to write an equation relating them. And I'm thinking similar triangles again. I can see that the base here to the height here, so the ratio of x to 6, is the same as the base of the larger triangle to the height of the larger triangle, which is x plus y over 20. Seem all right? Okay. I could differentiate both sides right now, but I could also do a tiny bit of work to make it a little bit nicer. I could cross multiply. 20x equals 6x plus 6y. And I could bring all my x's to the left. 14x equals 6y. It seems a little nicer. It's totally unnecessary, but it does make it easier to deal with. So now if we differentiate, the derivative of 14x is going to be 14 times dx dt. And the derivative of 6y is going to be 6 times dy dt. Now I'm going to plug in what I know, solve for what I don't. And the dy dt is 4 feet per second. So I'm going to have 14 times dx dt equals to 6 times 4 feet per second. So it looks like dx dt is going to be 24 over 14, which reduces to 12 over 7 feet per second. And just notice, nowhere did I ever use the information that she was 10 feet away from the lamp. So similar to that problem where we were filling up the cylinder with water, here it also doesn't matter how far she is away from the lamp. She can be 10 feet from the lamp, and as long as she's walking at 4 feet per second, her shadow is increasing in the length of 12 centimeters per second. Or she can be 20 feet from the lamp, or however far from the lamp, assuming that her shadow is still like being cast, right? We're not pretending like this is a real thing or anything like that. So as long as she is walking at 4 feet per second, her shadow is always increasing at 12 sevenths of a foot per second. Which kind of makes sense if you think about it, because again, the shadow is just some ratio of how tall she is and how the light's being cast. Now, I will point out that I've seen a question like this in the 21A textbook, but it's phrased slightly differently. An alternate phrasing of this question, which leads to a different answer, is the following. Some people like to ask instead, how fast is the tip of her shadow moving? When she's it doesn't matter how far, it's still not dependent on how far she's away, but you could say when she's 10 feet from the lamp. Okay. There's an easy way and a hard way to do this. The hard way is to redo the whole thing. The easy way is to do all the work we've already done and then say, okay, I want to know how fast the tip of her shadow is moving. Well, how fast is her shadow growing? 12 sevenths of a foot per second. How fast is she walking? 4 feet per second. Add those together, that's how fast the end of her shadow is moving. Right? The rate her shadow is moving at is just how fast it's growing plus how fast she's walking. Now, we can be a little more precise about that. What I'm really asking about is how fast this point is moving away from this stationary point. So I can really say, okay, I'm really asking what's the derivative of x plus y. I want to know how fast this length is increasing, because that tells me how fast this point is moving. Well, great. I know how to take the derivative of the addition of two things. It's just the derivative of the first thing plus the derivative of the second thing. And from all the work we already did, we know both of those things. We know that dx dt is 12/7 of a foot per second. We know that dy dt is 4 feet per second. So adding those together ends up being 40/7 of a foot per second. So if you see a shadow question like this, be aware of the phrasing. It's a different question to ask how fast is the length of the shadow increasing versus how fast is the tip of the shadow moving. But if you answer the first question that I asked, it's very, very easy to then answer the second question about the tip of the shadow. You just add on how fast the person is walking. What's that other example here? What's that? Oh, okay. Sure. I know where you are. Go back there. Yeah, let's do that one. That's a good one. So let's say we got the following. Mia is standing 8 feet from her sister, Gabriella. Gabriella lets go of a balloon. That rises at 2 feet per second. How fast is the distance from Mia to the balloon changing 4 seconds? Oh, sorry, not 4, 3 seconds after Gabriella let go of it. Okay. So, right, I mean, these problems, they might start to feel somewhat repetitive. Right? It's very much this thing is right, something's happening, something's moving. I should say they probably are starting to feel repetitive to me because I've seen them so many times for so many years. They're probably not feeling that repetitive to you. But what I want to emphasize is the process should be repetitive. It should always be the same 4 or 5 steps where we first draw a picture if we can, then figure out what's changing, write an equation, differentiate both sides, plug in the things we know, right? Those are like the 4 big steps. So, well, I mean, drawing the picture is also a big step. Let's draw the picture. So here's Mia, here's Gabriella. They're standing 8 feet apart from each other. And Gabriella, sorry, here's Mia, here's Gabriella. And Gabriella, let's go for a balloon. Oh no, there's a balloon. And this height of the balloon, that's changing, right? We're going to give it a variable name. And the distance from Mia to the balloon is also changing, right? Because the balloon is moving. And we're going to call that distance, I usually call a diagonal distance S. I don't know why, it's just what's been ingrained in me. Some people call it Z. Nobody ever calls it D, right? For whatever reason, you will never see anyone call like a distance that we're going to take a derivative of D. And I think it's because nobody wants to write dt. It just feels really weird to be like, okay, if the distance is D, the derivative would be dt. No one's writing that. I don't know why. I mean, I feel like I know why. I feel like it just looks dumb. like to be right. There's no good reason, but nobody does it this way. So diagonal distances, for whatever reason, don't call them D. No one does it. Or be a rebel in college. Be like, I'm going to do whatever I want. So there's our picture. Let's identify what's changing. We know that the height of the balloon is changing. At the rate of change of the height, or the rate of change of the distance from this stationary person to this thing that's moving, is just how fast the balloon is changing its position, which is 2 feet per second. And then we want to know what ds dt is. Do we expect ds dt to be positive or negative? Is the distance of the balloon increasing or decreasing? Definitely increasing. If it helps, like if you're not sure, you can always draw like a second picture where the balloon is higher and be like, oh yeah, it looks like it's further away. So it should be positive. It's good to think about if your answer should be positive or negative. Second part, we're going to write an equation. Again, relating the variables we want. Here, it's not similar triangles, right? I don't have another triangle to be similar to. What famous theorem do I need to use to write the equation here? Yeah. So I'm going to say 8 squared, because 8's not changing. That distance is always 8, plus the height squared is equal to s squared. And now we're going to differentiate both sides. Implicitly. That's what we always do. What's the derivative of 8 squared? Thank you. Yes, it's a big old 0. And the derivative of height squared is there's some stuff squared, which is 2 times your stuff to the first times the derivative of your stuff. And it's equal to the derivative of s squared is 2 times your stuff to the first times the derivative of your stuff. And now we're trying to figure out what this is. So we should be able to substitute in for everything else. And that's generally the gist, is once you identify what you're trying to solve for, everything else should be a known quantity. So when I plug in, let's see, do I know what the height is? I mean, it should. Well, I know the balloon's been rising for 3 seconds. And its rate has been 2 feet per second. So how high is the balloon? 6 feet. Oh, and I know what dHdt is. I know it's 2 feet per second. And then do I know what S is? Well, no, but I have an equation where I could find it, right? Even though I don't know what S is right off the bat, if the height is 6 feet, which it is at this particular moment, then I can say, oh, 8 squared plus 6 squared equals S squared. And we can solve for S. And not all the time, but a lot of the time they're going to make the numbers nice. 8 squared is 64, 6 squared is 36, and 64 plus 36 is 100. So S has to be 10. And what you might see here is what we really have is a 3, 4, 5 right triangle going on. So if you look at this 3, 4, 5 triangle, and you multiply all the sides by 2, you have a 6, 8, 10 triangle, which is exactly what we have. We have a 6, 8, 10 triangle. So if you can see, like, for example, if you saw that the legs of your triangle were 30 and 40, you'd automatically be like, oh, I know the hypotenuse is 50. Because it's still a 3, 4, 5 triangle just multiplied by 10. So you should be aware of 3, 4, 5 triangles and their multiples, like a 6, 8, 10, or a 60, 80, 100, or a 6,000, 8,000, 10,000. Right? All of those are still 3, 4, 5 right triangles, just multiplied by some constant. And then we're going to solve for ds dt. So divide both sides by 2, divide both sides by 10 feet, and you get 6 times 2 is 12. Divided by 10. It is going to be feet per second because the feet here cancel with the feet there. Or simplifying even further, ds dt is 6/5 of a foot per second. I suppose you could say 1.2 if you prefer decimals, but I prefer fractions because I just do. That's our answer. No, we'll save the bonus question for the next one. Okay. Let's ask another question that has also a right triangle kind of thing. So let's say we're flying a kite. James is flying a kite. And I'm flying a kite like a pro, meaning I'm keeping the height of the kite, that rhymes more. Flying a kite at a constant height above the ground of 40 feet. But the wind comes up. The wind pushes the kite horizontally away from me. At 10 feet per second. So the idea here is, right, the kite is at some height and it's moving just away from me this way, but it's not like changing its altitude. It's still staying at the same height. I know it's not very realistic, but neither are any math questions you're ever going to see are really realistic. So, and that's not entirely true. You'll definitely see realistic math problems some of the time, but probably not in your math classes, to be honest, right? You'll see the realistic math problems in your other classes where you're using the math to do real things. How fast do I need to let out the string when the kite is 50 feet away from me? Okay, let's do some labeling. Let's draw a picture before we do some labeling. So here's me and my kite. I was flying, let's say, directly overhead. So here's where my kite started, 40 feet above my head. But then it got pushed horizontally away. To some point over here. And still moving that way. So I know that this length is changing. And I know that this length is changing. But it really, so I guess it's important, right? Like you might not have thought about the kite being directly overhead. You might have just thought about moving this way, but it kind of need a reference point to be like, oh, from here to here, the kite's moving at 10 feet per second. So I can say that this distance from here to here is changing at 10 feet per second. Same kind of idea as before. A little different though. So there's a bit of a difference here that I want to make extra clear. So we're going to, of course, ask what's changing. We know that dx dt is changing at 10 feet per second. And we're being asked to find how z is changing, or what dz dt is. All right. We're going to write an equation. It's going to be the same equation as last time, still the Pythagorean theorem. 40 squared plus x squared equals z squared. And it's still the same sort of derivative. I'm going to take the derivative, I get 0 plus 2 times x times dx dt equal to 2 times z times dz dt. And I will point out, you could totally cancel these 2's right off the bat. All right, so now plug in. All right, so what's what? Well, I'm going to leave the spot for x and the spot for z alone for a second. I canceled the 2, sorry. So I know that dx dt is 10 feet per second. And I know that dz dt is what I'm trying to find. But which of the things am I actually knowing? do I know what X is or do I know what Z is? Well, the question says, how fast do I need to let out the string when the kite is 50 feet away from me? Which of those variables represents that? Is X how far the kite is away from me, or is Z how far the kite is away from me? Well, here's me. Here's the kite. It is Z. It's actually how far the kite is away from me. So it's meant to be a tiny bit misleading, right? So when we're talking about distance between things, like in the previous problem, not the previous problem, the previous problem, right, when I was talking about the distance from like Katie to the lamp, we meant the horizontal distance, right? Because the lamp is kind of like, it's a whole big thing, right? It's not at one point, it's kind of all here. So you're saying, oh yeah, we're just talking about that distance being 10 feet. But here, when you're talking about my distance to the kite, well, I'm here, the kite's up there, it's got to be this diagonal distance. So we're actually plugging in Z equal to 50, which is nice, because if Z equals 50, everybody should be able to hopefully tell me that X is going to be what nice multiple of 10. It's going to be 30. It's a 3, 4, 5, or a 30, 40, 50 right triangle. You're going to see these a lot. The other one you might want to know, just because it comes up semi-frequently, is a 5, 12, 13 right triangle. That's kind of the next well-known Pythagorean triple. So and then divide both sides by 50, you're going to get dz dt. Let's see, 30 times 10 divided by 50, or 30 divided by 5 is going to be 6 feet. You can go over a bit of implicit. Yeah, sure. Yeah. Let me. So I have one. I have a bonus question to follow up this example, and then we can certainly talk about some more implicit derivatives. I should point out, right, all these problems we've done, we've been using implicit differentiation, also known as the chain rule, right? Because I'm saying, oh, x squared. Really, if you want to think about it this way, x is a function of time, and z is a function of time. So you take the derivative of some stuff squared, you get 2 times your stuff times the derivative of your stuff. And the derivative of stuff squared is 2 times the. But yeah, we can definitely use some examples of that. So, but there's a bonus question I want to ask you guys, which is, okay, same situation, but now I want to know, in this situation, where the kite, right, is going that way, how fast is the angle of elevation from James to the kite changing? So I'm really asking, how is that angle beta changing? I should say, how fast is it changing when the string is still 50 meters out? 50 feet, sorry. Right, where the kite is 50 feet from James. And it's written a different way, sorry. So I want to know what's going on there. So I'm still going to call this X, and this Z, and this 40. And now I really want to know how fast this angle is changing. Well, it might be easier to deal with if I remember that this angle is the same as this angle. I know there's a theorem, but I think it's called like the alternate interior angle theorem or something. It's been years since I've seen those words. But yeah, it's the same. So I'm trying to figure out, well, let's see. I want to figure out what's changing, or what I want to know is changing. So I want to know how beta is changing. And what do I know? I know how X is changing. technically, we also know how z is changing at that moment. But here's what I want to point out to everybody. No matter where we are in this problem, dx dt is always 10 feet per second. On the other hand, it's only precisely at the moment when z equals 50 that dz dt is equal to 6. So yeah, we know that dz dt is equal to 6 feet per second, but only exactly when z equals 50. You can totally use that, but generally when we're doing this kind of type of thing, we try to use things that whose rates of change are, we know are always the same. It's just a better practice. You can totally do this next part using this other piece of information, but I don't really want to. Because then so here's why. I could ask you the question, well, what's it going to be when the string is 100 feet now instead of 50? And then this piece of information would no longer be useful at all. So great, we know what's changing and what we want to know is changing. Now we need an equation relating the variables of interest and preferably no other variables. So let me ask you all, what trig function could we use that's going to relate the angle theta, the side x, and preferably not the side z? And there's two valid choices here. I know I've drawn my triangle in kind of a way that makes it hard to figure out. Let's see, I want this angle and I want this side and not that side. This side we usually call the what? And this side's the, so we want a trig function that has the opposite and the adjacent. That's going to be, tangent is definitely one option. You could say tangent of theta equals 40 over x. But knowing that I'm going to differentiate both sides of this equation, I would like to make my life easier. So instead of using tangent, I'm actually going to use cotangent of theta, which is the adjacent over the opposite. Cotangent is just the reciprocal of tangents. And really what I'm actually going to do is I'm going to multiply both sides by 40. So that 40 times cotangent of theta equals just x. And now I'm going to look ahead towards what I know is going to happen because it can be a little bit confusing. I want to point out that tangent of theta doesn't really have any units associated with it. 40 feet divided by x feet doesn't have any units. There's no dimension there. And that's true about trig functions, right? Trig functions are always just really ratios. They're one length divided by another length. So when we find this ratio, it's going to be this thing. Well, there is a, I always feel like I interchange the word units and dimension kind of inappropriately sometimes. There is a unit that doesn't have any dimension to it. You guys all know what, well, you guys all know about it. You might not know what it is. The unit is radians. So think about radians for a second. When you find an angle using radians, you're really talking about, let me ask everybody, what's the, I know this is going to sound like an easy question to answer. How many radians are in a whole circle? How many? How many degrees are in a whole circle? 360 degrees. How many radians are in a whole circle? 2 pi radians. And the way you get that measurement is you taking the circumference of the circle, right? The whole circle, which if your radius is, I don't really care. Let's say your radius is 4 feet. The circumference is 2 pi times 4 feet, which is 8 pi feet. And the radian angle measure is literally the arc length of the circle, in this case, the entire circumference of the circle, 8 pi feet divided by the radius of the circle, which is 2 pi radians. So when you have this unit without dimension, it's radians. That's what I'm trying to make super clear, is that when we talk about this value over here, tangent of theta equal to 40 over x is measured in radians. Yeah, so that's what I'm like, I mean, really it's the angle that's measured in radians. Okay. So we'll come back to that in just a second. Let's go ahead and do what we're going to do. We're going to find the derivative, right? Because we're being asked to find d theta dt. So I've got 40 feet times the derivative of cotangent of theta, which is negative cosecant squared of theta times d theta dt equal to dx dt. And now we're going to plug in and solve. So I got 40 feet times some stuff equal to dx dt, which is 10 feet per second. All right, and let's figure out what this stuff is here. So negative cosecant squared of theta. Well, I know that sine of theta is the opposite of the hypotenuse. And what's the hypotenuse length at the moment we're interested in? Oh yeah, it was 50. So sine of theta is opposite of hypotenuse, which is 40 over 50, or 4/5. Which means cosecant of theta is going to be the reciprocal, 5/4. So cosecant squared is going to be 5/4 squared, which is 25/16. There's the wages, sorry. And now we can simplify. I can cancel a 4 here, and a 4 here. I'm left with 250 over 4. I can actually just cancel a 10 here and a 10 here. So solving for d theta dt, I get negative 4/25. But feet divided by feet give me just blank per second. And this is where you have to be like, oh yeah, when you don't have a dimension, you don't have a unit there, it's radians. Because feet per feet, just like here, when you find 8 pi feet per 4 feet and you get 2 pi radians, that's what we have here. The shorter answer to this is when you're finding how an angle changes, your unit should always be radians per some time unit. Never ever degrees. Unless you want to change it to degrees. Or you totally could take this and multiply it by 360 degrees over 2 pi radians to change it to degrees, but that's nothing you want to do. Also, interestingly, not that interesting if you look at the picture, the angle of elevation is increasing or decreasing? Decreasing, right? Because the further out this thing moves, the shallower that angle is going to be. I do encourage you when you do these related rates problems, especially if your answer is negative, to think about if that actually makes sense. Does it make sense that the thing that's changing is getting shorter? I'm not going to do this example, but I'll just point out, I know I've seen a problem recently where you've got like this ladder sliding down a wall. Here's the ladder. And if you call this distance y and this distance x, and it's sliding down this way and out that way, you should definitely, in your setup, depending on which thing you're given, it should be true that dy dt is negative because the length of y is decreasing. And it should also be true that dx dt is positive because the length of x is increasing. It's just good to think about whether things are getting smaller or bigger when you're figuring out what the rates of change are going to be. Okay. Oh yeah, I was going to do a question like that. I know we're short on time. Well, we're not short on time. We've used a lot of the time we have today, and there's not much left. Well, let's talk about a couple interesting examples of doing some implicit differentiation. So let's say we had something like this. Yeah, I got lots of good examples here. Let's say we have e to the x cubed times y equal to 7x plus 4y. And we're tasked with finding y prime. When we see this, you should automatically think, oh, y is a function of x. Even if it's not actually true, it's probably not actually true. The whole idea here is that we're going to use the chain rule, just like we have before. So what's the derivative of e to the stuff? What is the derivative? Well, the derivative of e to the x is e to the x. The derivative of e to the stuff is e to the stuff times always, right? That's whenever we say stuff, we know we're multiplying by the derivative of the stuff if we're taking derivatives. So the derivative of e to the stuff is going to be e to the stuff times the derivative of the stuff, which I'm just going to write literally as the derivative of the stuff. And on the right-hand side, the derivative of 7x is going to be 7. All right, take it easy. Oh, make sure you fill out the attendance form if you didn't before already. Oh, I didn't change it to the other ones. You want to flip it over and fill out the attendance form, or you can just grab it later on. It's on Canvas if you want to. You can also just do it right now. Thanks. Yeah. Sorry about that. Also, here's for everybody else too, in case I didn't give you guys the attendance form. Well, I think I did. Here's the attendance form. Fill it out when you have a sec. Sorry. So the derivative of 7x is 7, and the derivative of 4y is 4y prime. Let's do one more step. Well, we need, of course, at least one more step. For x cubed times y, the derivative of x cubed times y, we're going to have to use the product rule. The derivative of x cubed is 3x squared. We'll leave the y alone. And then leave the x cubed alone, and the derivative of y is the derivative of y. In this sort of situation, we really need to distribute. Because algebraically, if we're trying to solve for y prime, we need to be able to group the y prime terms together and the not y prime terms apart from that. And this thing right here is kind of jamming that up. You can't really, the only way to deal with this is to distribute this here. So I'm going to have 3x squared y times e to the x cubed y plus e to the x cubed y times x cubed y prime equal to 7 plus 4y prime. And then I'm like, okay, here's a y prime term, here's a y prime term. Let's put all those on one side, everything else on the other side. It doesn't matter which side you pick. If we pick different sides, our answers are going to look a little different. I usually pick everything to go to the left for a y prime. So I'm going to have e to the x cubed y times x cubed y prime minus 4y prime equal to 7 minus 3x squared y e to the x cubed y. Factor out a y prime. You're left with all the other stuff, e to the x cubed y times x cubed minus 4. Still equal to the same stuff on the right-hand side, 7 minus 3x squared y e to the x cubed y. And then finally, divide by all this here. So that our derivative y prime is 7 minus 3x squared y e to the x cubed y over e to the x cubed y times x cubed minus 4. It's not so much that these problems are difficult to differentiate. It's just the algebra is kind of gnarly, right? You have to be careful keeping track of everything here. Let's look at another example. We got 11:48. Yeah, we can do one more. Because there is something I don't want to say forgot, but yeah, I know forgot's fair. Something I kind of forgot to mention or talk about. Let's say we have this example. We want to find the second derivative for the equation, I don't know, 4xy plus 7y squared equal to 9. I'm gonna make my life a little easier, I think, and make this 7 and 8. I think something might divide a little bit more nicely if I do that. So how do we find the second derivative? Well, to find the second derivative, you almost always have to find the first derivative first. So let's go ahead and find the first derivative. We're going to do it implicitly because that's the only option we have. So the derivative of 4xy. So here's again, to the person who asked me before, like, why did I keep the pi as a multiple of just the first part? Because I find it convenient to, right? You could think of this as 4 times the quantity xy and use the product rule. I would really rather think of it as 4x times y. It just seems easier to me. If it's not easier for you, don't do it that way. So derivative of 4x times y is the derivative of 4x times y plus vice versa, the 4x times the derivative of y plus the derivative of 8y squared, which is going to be 16y times y prime equal to 0. And then we're going to solve for y prime. So all my y primes are already on the left. Let's bring the non-y prime thing over to the right. Also, since they're already on the same side for the y primes, let's go ahead and factor them out. So from this piece here, and the factor of the y prime, I'm going to be left with 4x plus 6y, and it's going to equal negative 4y. Now I'm going to divide both sides by this. So I'm going to have y prime equal to negative 4y divided by 4x plus 16y. And in this case, I would divide the top and bottom by 4 and write it as y prime equal to negative y over x plus 4y. Not necessary, but probably helpful if I have to do more work after this, which I do, because I have to find the second derivative. All right, so when we find the second derivative, it's just the derivative of the first derivative. So y prime, sorry, not y prime, d squared y dx squared is just going to be the derivative of y prime. So that's going to be, and if you got to go, you got to go. Totally understand. You guys too. If you got to go, you got to go. I'm just going to finish this problem. So the derivative of y prime, I'm going to do the derivative with respect to x of my quotient, negative y over x plus 4y. And pretty much like 99 times out of 100, or maybe 999 times out of 1,000, your first derivative for y prime almost always is going to be a quotient. Because if you're doing this sort of algebra, you're almost always doing this thing where you're bringing the y primes to one side, you're factoring out, and you're dividing by what's multiplying y prime, meaning y prime is going to equal something divided by something else. So it's always going to be a quotient, or almost always going to be a quotient, meaning you're going to have to use the quotient rule. So it's going to be the bottom times the derivative of the top. Now be careful. The derivative of negative y is negative y prime minus the top times the derivative of the bottom. The derivative of the bottom is 1 plus 4y prime, all divided by the denominator squared. Okay, here's where things are a little bit dicey. We know what y prime is equal to. Y prime is negative y over x plus 4y. And what we really honestly should do is replace each y prime with what it's equal to. That's where things are a little bit funky. So our answer is actually x plus 4y times negative, negative. I'm going to make that positive. So I'm going to make that a positive y over x plus 4y. That's my negative y prime right there. Minus and minus is plus y times 1 plus 4 times y prime, which is negative y over 1 plus 4y. All over x plus 4y squared. Sorry, I wrote a 1 there. It should be an x. Apologies. which looks just incredibly ridiculous. You probably could do some simplifying here. You probably don't really want to. Sometimes with these second derivatives, you'll see the book like has some bizarrely simplified answer. What often happens, words, can I get the words out of my mouth? What often happens is somehow this equation pops back up in your answer. And like maybe our answer has a 4xy plus an 8y squared, and it gets replaced with 9. I feel like I owe you at least the opportunity to maybe set. So let's do some real quick simplifying here. Check this out. That cancels with that. So I end up with y, and then blah. I have plus y, and then minus 4y squared over x plus 4y, all over x plus 4y squared. I don't see anything particularly useful, but here's what I might do. I would probably try to get rid of this fraction here. So I'd probably multiply the entire top and the entire bottom by x plus 4y. It's a pretty standard move. So when I do that, I'm going to have 2y times x plus 4y minus 4y squared all over x plus 4y. And then if I do one more step, and then we're going to call it a day, I'm going to have 2xy plus 8y squared minus 4y squared. Oh, it does work out. It's kind of cool. It's not that cool, but okay. It feels like at least we didn't waste our time. So let me show you what I mean by what kind of works out. So if you look at this top part here, I'm going to simplify that as 2xy plus 4y squared all over my denominator. But now check this out, everybody. We know from our original equation that 4xy plus 8y squared equals 9. And that's almost the top. If I just divide this by 2, it's equal to that. So it is actually true that 2xy plus 4y squared equals 9/2. So if you were doing this problem and you got to say like right here, which is a totally fine place to stop in my mind, and then you looked in the back of the book, the back of the book answer might be something like 9 over 2 times x plus 4y to the third. And you might be like, how the heck did they get that? This is how. They did all the simplifying, and then they looked and saw, oh, look, my original equation is essentially popping back up. That's what they're doing when they make that simplification.